ನಾನು ಬೇಕಾದ್ರೆ ವಿಡಿಯೋ ಕಾಲ್ ಮಾಡಿ ತೋರಿಸ್ತೀನಿ ನಿಮಗೆ ಅದರಲ್ಲಿ ಸರಿ ಸರಿ. Hello, good evening, students. So in the today's class, let us continue the atoms MCQs. So in the last class, we have solved some few questions. In this session also, we'll go with the continuation of that atoms chapter. Look up this problem now, students. Now, the ratio of the kinetic energy to that of total energy of an electron in the Bohr orbit is. They're asking you to find the ratio of the kinetic energy to that of the total energy of an electron in the Bohr's orbit. Students, you know the formula for the total energy of the orbit, that is minus mz squared e power 4 divided by 8 epsilon naught squared n squared h squared. You know that the total energy goes with negative sign, which indicates that the electron is bound to the nucleus. That means you require an energy to remove the electron from the hydrogen atom. So this is the total energy formula. And what is the kinetic energy we got? We got the same value of total energy, but with a positive sign. It will be mz squared e power 4 divided by 8 times of epsilon naught squared n squared h squared. So total energy and the kinetic energy are the same formula in magnitude, but in the sign it is positive and negative. So if I take the ratio of kinetic energy by the total energy, the values will be the same. The magnitude will get cancelled out, but this will be minus 1, this will be plus 1. So the kinetic energy goes to be plus 1 and total energy goes with minus 1, which is going to be minus 1:1 ratio. So what is the ratio of the kinetic energy to the total energy? So the ratio of the kinetic energy to the total energy is minus 1:1. Therefore, option A will be the right answer, isn't it? Yeah. And without writing these formulas, and also you can tell directly, the ratio of kinetic to total is always a negative sign. It should be go with a minus sign. And look at the option. Among the 4 options, only one option is having minus, right? So that must be the answer. I hope you got the problem, students. Yeah. Come to the next one. There is an electron here. This electron is in the first orbit of an hydrogen atom having a energy 13.6 electron volt. So this is the energy in the first orbit. That means in the ground state. Now hydrogen atom is n equals to 3 state, third state. How much of energy is required to ionize it? You know that the energy in the nth orbit is directly proportional to E1 divided by n squared. Whatever the energy is there in the first orbit, for that if you divide it by n squared, where n is the orbit number, that gives the energy in that particular orbit. Now what is the question? They are expecting you to find the energy in the third orbit. So energy in the third orbit. What is the energy in the first orbit they have given? 13.6. That whole thing divided by n squared. What is n squared? 3 squared, 9. So E3 is equal to, what is 13.6 divided by 9? It will be 1.51 electron volt. So what is the energy in the third orbit? 1.51 electron volt. That is option D. So option D is the right answer. Yeah. Come to this particular case. Electron is going to jump from first orbital to the third orbital. So you know that this is the n equals to 1 state, n equals to second state, n equals to third state. You know that if electron has to move from the first orbital to the third orbital, you have to supply the energy. So the electron has to absorb the energy. The electron has to absorb the energy when it is moving from lower orbit to the higher orbit. If the same electron is coming from the third orbit to first orbit, it will emit the energy. It will emit the energy. So energy is going to emit when the electron jumps from higher orbit to the lower orbit. The electron is going to absorb the energy when it is moving from the first orbit to the third orbit. So now they are clearly mentioning that the electron is going to jump from the first orbital to the third orbital. Then it should absorb the energy or it should release the energy. Yes, when it comes from lower orbit to higher orbit, it should absorb the energy. So option A is the right option. When it comes from higher orbit to lower orbit, then it has to release the energy. No gain in the energy means the electron is itself in the same state, same orbit. Yeah. Look at this problem. The ratio of the frequencies they are expecting. The ratio of the frequencies they are expecting for the long wavelength. Long wavelength means energy must be low, because you know that energy is equal to hc by lambda. E is inversely proportional to the wavelength. So in order to get the longest wavelength, the energy must be the minimum. Energy must be the minimum. Now, for which series you have to find the ratio of the frequencies? For Lyman series and for Balmer series. Since you are going to find the longest wavelength means the energy must be a minimum. The energy is going to be minimum for the first line. So for the first transition, or for the first line, for the first transition or for the first line, we call it as a longest wavelength. We'll call it as a longest wavelength. First thing they are expecting for the Lyman series. For Lyman series, the electron has to come to the first state. From where it has to come for the first transition? First transition is from 2 to 1 for the Lyman series. 2 to 1 for the Lyman series. What about for the Balmer? What about for the Balmer? For Balmer series, the first transition is from where to where? Balmer means it has to come from the second, any orbit to the second orbit, right? So Balmer series, the electron has to take a transition from higher state to the second state. Higher state means what? The first line. The first line means 3 to 2. So Lyman series has to belongs from 2 to 1. Balmer series as belongs from 3 to 2. This is the first line of the Balmer series. This is the first line of the Lyman series. Now, you know the formula for 1 by lambda. 1 by lambda is equal to R into 1 by N1 square minus 1 by N2 square. But they are expecting to find the frequency ratio. Frequency ratio. You know that 1 by lambda is nothing but, in terms of energy, you know that h nu is equal to hc by lambda, isn't it? Here h and h will get cancelled. Nu by c is equal to 1 by lambda. So 1 by lambda is directly proportional to the frequency. So 1 by lambda can also be taken as the frequency nu. So 1 by lambda can be taken as nu by c, but I'm taking only nu because it is a proportionality limit. So nu is nothing but R into 1 by N1 squared minus 1 by N2 squared. Now, can you write the frequency for the Lyman series? R into 1 by. For Lyman, it has to come from 2 to 1. So it is 1 by 1 square minus 1 by 2 squared. New Lyman is equal to R into 1 minus 1 by 4. This is equal to R into 1 minus 1 by 4 is what? 3 by 4. So the Lyman series frequency is R into 3 by 4. Now, what is the frequency of the Balmer? Similarly, R into, for Balmer, it has to take a transition from 3 to 2. So it is 1 by 2 squared minus 1 by 3 squared. So new Balmer is equal to R into 1 by 4 minus 1 by 9. That is R into 9 minus 4 is 5 divided by 36. This is the frequency of the Balmer series. So we have calculated the frequency of Lyman series to the Balmer series. Now, can we calculate the ratio of that? Can we calculate the ratio of that? The ratio of the frequency of Lyman to that of Balmer. That is 3R by 4 whole thing divided by 5R by 36. R and R will cancel out. So this will be 3 by 4 into 36 by 5. 4 ones are 4 nines are. So that will be 27 divided by 5. So what is the ratio of the frequencies? 27 is to 5. So you can go ahead with the option A. I hope you understood this problem, students. They are expecting you to find the frequency ratios for the Lyman series to that of Balmer series. That is equal to 27 is to 5. So option A is the right answer. You got it? Yes. Let us move on to the next problem. Now they are expecting to find for which transition in the hydrogen atom emits the photon with the highest frequency. They want the highest frequency. Yeah. Now, what is the formula for the energy? Energy is equal to H into nu. So this clearly tells Yeah. Sorry, students. Maybe some interrupt in the internet. Yeah. The hydrogen atom that is going to emit the photon of the highest frequency. So which is going to emit the highest frequency, you have to find. You know that the energy is equal to h into nu. So clearly that tells energy is directly proportional to the frequency. More the frequency, more the energy. So here they are talking about the first orbit. So I will go with E1. You know that the energy in the first orbit is minus 13.0 volt. Now I will find what is the energy in the second orbit because they are expecting in the second orbit also. You know that energy is inversely proportional to n squared. So clearly if you want to find the energy of the second, for this value you have to divide by 4. So it should get minus 3.4 electron volt. So what is the energy in this sixth orbit? I will calculate because here they have given 6. So for E6, how to calculate E6? It is E1 divided by 6 squared, that is 36. So 13.6 divided by 36. You have to divide that. 13.6 divided by 36. You will get around 0.38, close to 0.38. So it is minus 0.38. Yeah. Now, in order to go with the emission, it is emitting, right? Emitting means the electron has to jump from higher orbit to the lower orbit. Higher orbit to lower orbit means it has to come from 6 to 2. 1 to 2, 2 to 6 are not possible. Because from 1 to 2 or 2 to 6, the energy has to absorb. If the electron is moving from lower orbit to higher orbit, in the problem they are telling it has to emit. In order to emit, the electron has to move from higher orbit to the lower orbit. Higher orbit to the lower orbit, 2 to 1 or 6 to 2. But look at the difference. From 2 to 1, what is the difference? It is approximately 10.2 electron volt. Difference between 6 to 2, it is 3.4 to 0.38. It is close to 3.1 or close to 3.0 electron volt. So energy gap between 1 to 2 itself is more. Energy gap between 2 to 1 is more compared to the energy gap between 6 to 2. 6 to 2. 2 to 1 energy gap is more compared to the energy gap between 6 to 2. So clearly, what is your conclusion? For more energy, more frequency? No. More energy, more frequency. So to get highest frequency, you should get highest energy. So where is the highest energy? Highest energy is there in the 2 to 1 transition. Therefore, option B is the right answer. Option B is the right answer. Okay. Yeah. Look at this problem, students. In terms of Rydberg constant R, the wave number of the first Balmer series is. What is wave number? Wave number is nu bar, which is the reciprocal of the wavelength. What's the formula? It is R into 1 by N1 squared minus 1 by N2 squared. Now the first line of the Balmer series. First line of Balmer series. For Balmer series, the electron has to take a transition to the second orbit. First line means what? First line means it has to come from 3 to 2. First line means it has to come from 3 to 2. So what's the formula? Nu bar is equal to R into 1 by N1 squared, that is 3 squared, minus 1 by 2 squared, that is 1 by 9 minus 1 by 4. So R into 9 minus 4 is 5 by 36. If I take the LCM for 9 and 4, it is 36. Then it will become 1 by 9 minus 1 by 4, that is 4 minus 9, that is minus 5 by 36. Only the reverse we have done it. So N1 is the lowest number. If I say this is N2 and this is N1, then it will be 2 squared and it will be 3 squared. It will be 9 and it will be 4. But this will be the same. It is 5R by 36. So option C is the right answer. So this is 9. This is 4. So 9 minus 4 will be 5. 5 by 36. So this is nu bar. So this is the wave number of the first Balmer series. Okay. Come to this. Ionization potential of helium is 24.6 volt. Ionization potential is 24.6 volt means what is the ionization energy of the helium? 24.6 electron volt. So whatever the potential is there, that same potential we have to write it for energy, but instead of writing in terms of volt, you have to write it as electron volt. So 24.6 electron volt is the ionization energy of the helium atom. That means in the helium atom, if you want to remove the electron from that helium atom, we required a energy of 24.6 electron volt. That is the meaning of the value. Clear? Yes. Yeah, look at this 30th one. In the hydrogen atom, which of the following electron transition would involve the maximum energy change? Maximum energy change. So this is the first orbit. What is the energy in the first orbit? Minus 13.6 electron volt. What is the energy in the second orbit? You have to divide by 4. So that is minus 3.4 electron volt. What is the energy in the third orbit? You have to divide by 9. Divide by 9 means minus 1.54 electron volt. What is the energy in the fourth orbit? Because maximum is 4. 1, 2, 3, 4 and all are there. So what is the energy in the fourth orbit? You have to divide by 4 squared. That is divide by 16. That is minus 0.84 electron volt. So these are the energies in the first orbit, second orbit, and in the third orbit. Now, can you have the energy gap from 2 to 1? Energy gap from 2 to 1. 2 to 1 energy gap is this. That is 13.6 and 3.4 difference. That is 10.2 electron volt difference. So this gap energy is 10.2 electron volt. Similarly, can you find the energy gap from 3 to 1? 3 to 1 is this. This is 13.6 minus 1.54. It will be 12.1 electron volt. So energy gap from 3 to 1 is 12.1 electron volt. 12.1 electron volt. What is the energy gap from 4 to 2? This is 4 to 2 gap. That is 3.4 minus 0.84. That is close to 2.2. This is 2.2, which is very less. This is not possible because they are involving with maximum between 10.2 and 12.1. Even A is ruled out. Now calculate from 3 to 2. 3 to 2 is this, which is close to 1.9 electron volt. So between 12.1 and 1.9, even option D is ruled out. So for which transition the electron is having more energy? If the electron is taking a transition from 3 to 1, if the electron is taking a transition from 3 to 1, the maximum energy is going to be involved. That is 12.1 electron volt. So option B is the right answer. So option B is the ruled out. I mean correct answer. Yeah. Come to this 31st problem. Velocity of an electron in the second orbit of sodium atom is V. The velocity of an electron in the second orbit of sodium atom is V. Now they are expecting you to find what is the velocity of the electron in the fifth orbit. This is the velocity in the second orbit. Yeah. Very quite interesting problem, students. Now, you know that the velocity formula for the hydrogen atom is ZE square divided by 2 epsilon naught NH. How this velocity and N are related? Inversely proportional. Velocity is inversely proportional to the orbit number. Now, let us say this is the first orbit. This is the second orbit. This is the fifth orbit. Now you are asking you to find the fifth orbit velocity. They have given V2, that is V. We don't know what is V1, let it be X. But we want the answer in terms of V. In terms of V. How to write the velocity of the second orbit? V is inversely proportional to N. So for V2, you can take it as the velocity of the first orbit divided by N. Here N is 2. What is V1? X. X by 2. Similarly, can you write it for V5? V5 is V1 divided by 5. What is V1? V1 is X by 5. So V5 is X by 5. But I don't want the answer in terms of X. Look at the option. They have not given in terms of X. They have given in terms of V. So V1 by 2 is nothing but X by 2. So V2 will be X by 2. This implies X will be 2 times of V2, no? X value will be 2 times of V2, cross multiply. So in the place of X, now I can substitute as 2 times of V2. So 2 times of V2, 2 times of V2 divided by 5. 2 times of V2 divided by 5. So that is there in the option D. So option D is the right answer. Got it? Yeah. Yes. Look at the problem. The electron in a hydrogen atom makes a transition from N1 to N2, where N1 and N2 are the principal quantum numbers. Assume the Bohr model of the valid. The time period of the electron in the initial state is 8 times. T1 is 8 times that of the final state. T1 is equal to 8 times of T2. Now they are expecting you to find the possible values of N1 and N2. What are the possible values of N1 and N2? Yes. You know that the time taken is nothing but the distance by velocity. Since the electron is going to revolve around the nucleus in the atom, you can take the distance as one circumference, that is 2 pi r, divided by the velocity. You know that the radius is directly proportional to n squared and velocity is inversely proportional to n. So this n goes up, so it will become n cube. So time period is directly proportional to n cube. Time period is directly proportional to n cube. So what is T1 is equal to T2, or you can take this as T1 by T2 equals to what? 8. But the time period is directly proportional to the principal quantum number cube, n cube. So what is N1 by N2? I mean T1 by T2? T1 by T2 will be N1 by N2 whole cube, which is equal to 8. So what is N1 by N2? Cube root of 8. Cube root of 8. Or you can take this as 2 cube. 8 can be taken as 2 cube. To remove this cube, I will put 1 by 3. Cube root of 8. 3 will get cancelled out. So this value will be 2. N1 by N2 ratio should be 2. N1 by N2 ratio should be 2. N1 by N2 ratio should be 2. Now they are asking to find the ratio. Can you tell me the possible values? Look at this. Possible values of N1 and N2. 4 by 2, 8 by 2, 8 by 1, 6 by 3. N1 by N2 is 4 by 2, that is 2. This may be correct. 8 by 2 will be 4. This is not possible. 8 by 1, this is not possible. 6 by 3 is also 2. So this is also possible. So option A and option D are correct. Both options are true here. They are asking the possible values of N1 and N2. Possible values of N1 and N2 is 4 and 2, or it is from 6 to 3. Because the ratio should get N1 by N2 as 2. So that is possible in both the cases, that is option A and option D. Yes. According to the Bohr's model, what is the radius of the second orbit of helium atom? Radius of the second orbit of helium atom. Radius of the second orbit of helium atom. Yeah. Yes. Now, can you tell me what is the radius formula actually? Epsilon naught n squared h squared by pi m z e squared. So R is directly proportional to n squared by z times of the 0.53 angstrom. This is the general formula. If you want to find the radius of any orbit number for any atom in terms of radius of the Bohr's hydrogen atom, for radius of the hydrogen atom, you know that in the first orbit is 0.53 angstrom. Now, instead of analyzing for the first orbit, if you want to go for the any other than the first orbit and other than the hydrogen atom, then radius is equal to n squared by z times of radius of the first orbit, that is n squared by z into 0.53 angstrom. Therefore, can you tell me what is the radius of the second orbit of the helium? It is nothing but n squared by z value times of radius of the first orbit of hydrogen atom, that is 0.53 angstrom. Now, for which orbit you are talking? You are talking for the second orbit. So it will be 2 square by z. For helium, what is the value of z? 2. For helium, the value of z is 2. 2 squared by 2 times of 0.53 angstrom. So what is 2 squared? 4. 4 by 2 will be 2 into 0.53 angstrom. What is 2 times of 0.53 angstrom? It is 1.06 angstrom. Option B is the right answer. So students, you have to be very, very, very careful while writing the radius or velocity or total energy for hydrogen-alike atoms. Other than hydrogen, for helium, lithium, beryllium, if they're asking you to write the formula for the radius or velocity or total energy, you have to be very careful. So you have to remember this for radius. This formula is valid for any orbit number and for any atomic number. That means for hydrogen-like atoms. Yeah. Now, come to this particular case. They are asking you to find the extreme wavelength of the Pascal series. Extreme wavelengths of the Pascal series. Pascal means Lyman, Balmer, Pascal. So it has to come to the third orbit. Lyman, Balmer, Pascal. It has to come to the third orbit. Next orbit is 4. Then 5, 6, 7, 8, like that, up to infinity. Now, the extreme lines means what? The first line is from 4 to 5. I mean 4 to 3, sorry. The another last extreme line means from infinity to 3. So for first line, the transition has to be from 4 to 3. For last line, the transition is from infinity to 3. Infinity to 3. Yeah. Can you tell me the formula to find the wavelength? 1 by lambda equals R into 1 by N1 squared minus 1 by N2 squared. 1 by lambda first line is, R value is 1.097 into 10 power 7. 1 by 9 minus 1 by 16. Because N2 is 4, N1 is 3. So 1 by lambda 1 equals 1.097 into 10 power 7. What is the LCM? 1 by 9 minus 1 by 16. So what is the LCM for 16 and 9? It is 144. Then 16 minus 9 will be 7. So what is lambda 1 from this? It is 144 divided by 1.097 into 10 power 7 into 7. So how can you find this lambda 1 then? So lambda 1 is equal to how much? You have to do the calculations. What is the value of this? 144 divided by 1.097. Once again, you have to divide by 7. You will get 18.75. 18.75 into 10 power minus 7. Or you can take 1.875 into 10 power minus 6 meter. So 1.875 micrometer is the first wavelength. Look at the option, students. 1.85 is there. 1.85 is close to 1.89 is there. So definitely option B will be the answer, because in none of the options we don't have 1.8 something. So instead of calculating the second extreme line wavelength, we can tell the option which is the right answer. So option B is the correct answer. But if you want to find the wavelength of the last line, use the same formula. 1 by lambda last line, which is equal to R, that is 1.097 into 10 power 7. 1 by N1 squared, 1 by 9 minus 1 by infinity. Or if you want to find the wavelength of the last line, it will be 9 divided by 1.097 into 10 power 7. So if you divide that value by 9 divided by 1.097, you will get 8.20. 8.20 into 10 power minus 7. Or you can take 0.82 into 10 power minus 6. That is 0.82 micrometer. So the other extreme wavelength is 0.82 meter, which is close to 0.818 micrometer. So definitely option B is the right answer. Yeah. Yes, students, look up the last problem of this chapter. That is, hydrogen atoms are excited from the ground state to the principal quantum number 4. Then what are the number of the spectral lines absorbed? If the principal quantum number is 4, can you find the number of spectral lines? Students, have you remembered? I've given one shortcut formula for this in the synopsis class. Number of spectral lines, if you want to find, you have to make use of the formula n into n minus 1 divided by the 2. N into n minus 1 divided by 2. So what is n here? 4 into 4 minus 1 by 2. That is 4 into 3 divided by 2, which is nothing but 6. So how many spectral lines you can observe here? 6 spectral lines. Suppose if you want with a diagram L, by the help of the diagram also you can analyze this. If you not remember the shortcut formula, that is quantum number is 4. First line, second line, third line, and this is the fourth line. So for these 4 lines, you have to write the transition. Now, possible values are 4 to 1, 4 to 3, 4 to 2. This is one transition. Now, you can take the transition from 3 to 2 or 3 to 1. This is one sector. So, from 4 to 2 possible, from 3 to possible. Now, the another possible is from 2 to 1. So, this are the sector. So, 1, 2, 3, 4, 5, 6. So, how many possible values we have? 6 possible values we have when the electron is taking a transition from the fourth state. So if the electron is taking a transition from the fourth state, then the number of spectral lines will be equal to 6. You have to remember this. So option B will be the right answer. Got it, students? Yeah. So this completes the concept of the atoms chapter, students. So in the next class, I'm going to take up the new chapter, that is nuclei and radioactivity. So in this chapter, we have studied about the concept of the structure of the atom. You know that the central part of the atom is called the nucleus. Now we are going to study about the properties and the phenomena exhibited inside the atom, that is in the nucleus, and how the reactions is going to take place inside the nucleus, which you call it as a nuclear reactions. During that nuclear reaction, some radiations are going to be emitted out, which phenomenon we call it as the radioactivity. This we are going to deal in the next chapter, student, that is in the next class, that is nuclei and radioactivity. I will stop at this stage, students. Thank you.